So friction. Friction is another type of force. Specifically, it's a resistive force. So what it likes to do is resist the desired movement of an object. And it's actually something that's everywhere in our lives. So the computer you're watching this on is held together by screws and nuts and bolts. And without friction, all those screws and nuts and bolts would end up unraveling, and that would be very, very easy for your whole computer to fall apart. But it's not just new things. The knots in the fabric of your clothes are all held together by friction. So without friction, all those clothes would just become unraveled. The tires of your car, in order to move, there has to be friction between the tires of your car and the road. Otherwise, those wheels would just keep spinning. We wouldn't even be able to walk without friction, because in order to walk, what we end up doing is we use our feet to push against the ground. And if there was no friction to push against, then our feet would just free spin, kind of like those old Scooby-Doo cartoons. So there are two main types of frictions. There's static friction, and static friction is between two stationary objects. So this is where you've got stationary, nothing's moving. And then you've got kinetic friction. So if you think back to, you may have done kinematics. Kinematics is the study of motion. So kinetic is between two objects that are moving. But it's not just moving. A better way to think about it would be sliding or rubbing. Two objects that are sliding or rubbing. So you can actually simulate both of these cases using just your hands. If you put your hands together and you move them back and forth, as they're rubbing back and forth, you might feel your hands heat up. That is partially due to the friction between it. What you're actually doing is you're creating energy and it's changing it to thermal energy, but that's a later unit. But as you rub them together, you've got that kinetic friction. If instead you press your hands together and you start to try and move them, but not actually move them, you've got that static friction. So as you're pushing your hands together and you're trying to rub them together, but without actually rubbing them, you've got static. When you're actually rubbing your hands together, you've got kinetic friction. And a really silly physics joke for you, friction is fun. And it's not funny right now, but once you learn the equations, it will be funny-ish. Friction is fun because the equation for friction is mu n. So friction is F-U-N, friction's fun. Both of these are forces, so they're vector quantities. There are different equations for the different types of friction. So static friction is always less than or equal to mu n. And then kinetic friction, Fk, is always equal to mu n. So this fancy F is the friction, whether it's static or kinetic. The mu stands for coefficient of friction. Coefficient of friction. And then the the N is your normal force. It would help if I spelled normal force correctly. One thing to note about the mu stands for coefficient of friction, and it is a unitless, so it doesn't have any sort of units to it. No newtons, no meters per second, no kilograms, nothing like that. Mu is a unitless quantity. The other thing to know about the coefficient of friction is that it's always a small number. So if you've got a number that's like, if you've got a number that is less than 1, that's totally fine for the coefficient of friction. Normally the coefficient of friction will lie somewhere between 0 and about 1.5-ish. If you have something greater than 1, it's normally two very, very, very rough surfaces rubbing together. If you've got something close to 0, then you've got two very slippery objects. So based off of that coefficient of friction, you can find out if the object is pretty rough or if it's going to be pretty smooth. But again, it should always be less than probably 5. I've never seen any sort of coefficient of friction that's greater than 5 on any high school physics problem. And if you do find something that's greater than even 2, I might be backing at my work and figuring out what went wrong or what's going on. It should be kind of an extreme case. Normally, your sweet spot's going to be somewhere between 0 and 1. So let's take a look at an example here. We're going to go through 4 different examples, and if you haven't watched my video on normal force, I would strongly go back and watch those. because we're going to use nearly identical situations, and if you look here, we will have to calculate the normal force, so I'm going to just quickly go through those, and if you haven't watched that video on how to find the normal force, you might get a little bit lost. So strongly suggest going back and watching that before you finish up this video. So here's the first situation. A 6 kilogram box is at rest on the floor. Then it tells us the coefficient of friction, and it asks questions about will the box move. So first and foremost, what I need to do is I need to figure out what in the world is going on in this situation. So we've got a box on the ground. At some point, we're going to apply a force, and it should say horizontally, but this is just a practice problem that I just came up with at the top of my head. So that should say applies a horizontal force of those. So here's the situation, and we want to find out if it's moving. So does it have a velocity? And let's go ahead and draw out a free body diagram. If we're dealing with forces, it's always smart to draw that out. So we're near the surface of the Earth, which means we have a weight. We've got a normal force acting up. At some point, we're going to have somebody pushing it horizontally, so force of a person or force of a push. And then the friction is a resistive force. It resists that movement. So the person wants to push it to the right, which means friction is going to keep it from doing so. Ideally, that's going to be static friction because it's at rest. And we'll see what happens. We'll see how to figure out if it's moving or not. So the next thing I'm going to do is I'm going to write out my little chart. I suggest drawing out the situation, the free body diagram, and the chart in any sort of force problem, especially if you keep getting lost somewhere. In order to do that, I need to dictate my positives and negatives. I'm just going to use standard convention. So forces in the x direction, we've got the person pushing it to the right, and then we've got static friction pushing it to the left. In the y direction, we have normal force going up, and we've got the weight going down. One thing that we can say for certain in this problem is that the acceleration in the y direction will be 0. The reason I'm allowed to say that is because there's nothing else acting in the y direction. The person is pushing horizontally, so it might be accelerating in the x direction, but the person isn't going to be making the object accelerate off of the surface or into the surface. So I can confidently say that the acceleration in the y direction is 0. Well, if the acceleration in the y direction is 0, that means the sum of all the forces in the y direction should also be 0. And that comes from Fy is equal to, basically F equals ma, if I can write that down. Where if the acceleration is 0, then the net force is 0 as well in the y direction. So what dictates if something moves is that static friction. So if we look back at our equation, static friction is always less than or equal to mu n. So what I'm going to end up doing is, static friction is another one of what I call a lazy force. It only does as much as it needs to do. So if I'm pushing with 5 newtons of force, static friction will only give me 5 newtons of force back. If I'm pushing with 20, static friction will give me 20 back. If I'm pushing with 40, static friction will give me 40 back. But there is a maximum that it can apply. So there's only so much force that you can apply to it until that static force says, nope, I'm done, I can't do any more. And that's why there's that less than or equal to. So what our goal is we need to figure out what is that maximum static friction that we can apply. So they give us the coefficient of friction. They give us that this guy is 0.6. But they don't tell us what the normal force is, which is why it's so important that you go back and watch that previous video. We can determine what the normal force is by saying that the sum of all the forces in the y direction is 0, which means normal minus weight is 0. So our normal is equivalent to the weight, which in this case, if we plug in all the stuff, the normal force is 58.8 newtons. So now that I know the normal force, I can plug it in here. And I know that the static friction is going to have to be less than or equal to 0.6 times 58.8. So our static friction will always, always, always be less than or equal to 35.28 newtons. So if we look back at our problem here, if someone applies 5 newtons of force, well, 5 is less than or equal to 35, so nope, the object's not moving there. If we go to the 20 newtons is less than or equal to 35, which means yes, static friction can oppose that, so this guy's not moving either. But as soon as we get to 40 newtons is not less than or equal to 35. So static friction can only give 35 newtons, which means if the person pushes with 40, the object will start to move. And that's how that static friction works. It always opposes for as much as it can before it just says, I give up, you win, you can make this object move. So at 5 newtons, the object's static friction says, no, 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 you can't move. 20 newtons, still the same thing. But as soon as it hits 35.28 or higher, that object says, all right, fine, 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 fine. Well, I'll allow you to start moving. And that static friction becomes kinetic because now the object is sliding across the surface. So static friction only pushes as hard as it needs to. Let's go ahead and take a look at some kinetic friction work now. So here's again a very, very similar situation to the normal force problem that you guys saw in the previous video. Let's go ahead and draw out a picture of it. Again, at this point, I usually strongly encourage people to pause the video and try and figure this all out on their own. What I'm about to do is draw a picture of the situation, do a free body diagram, and write a chart, and then see what I can figure out from there. Strongly encourage you guys to pause and try that out on your own before I do it. So here is the situation. Box on the floor being pulled at a 30-degree angle. The free body diagram is the weight going down, normal force going up, the tension going at an angle, specifically a 30-degree angle, and a frictional force, specifically kinetic, because the object is being pulled. So here is our free body diagram. Last thing I need to look at is my chart, x and y. In the x direction, I have kinetic friction going to the left, and I have the x component, the x component of tension going to the right. In the y direction, I have normal force going up, I've got the y component of tension going up, and I've got weight going down. So if I want to figure out the magnitude of the frictional force, I ultimately need to figure out, all right, Fk is equal to mu n. As I look through here, I know that I will eventually need the coefficient, which is given to me, and I will eventually need the normal force. So as I look at this, I can see the normal forces in the y direction. So I ask myself if I know anything about the forces in the y direction. Well, again, it would be illogical, if you watch the previous video, it would be illogical for the person to be pulling on this box so hard that it lifts off the ground. So we can go ahead and make the assumption that the acceleration in the y direction is 0 meters per second squared. If that's incorrect, if that's a wrong assumption, then we'll quickly discover that as we're doing some calculations. I made up this problem, so I know that it's an okay assumption to make. But if the acceleration in the y direction is 0, that means the sum of all the forces in the y direction is 0 as well. So using the same information from the last video on normal force, I can find out that the normal force is equal to the weight minus the tension in the y direction. Going through and plugging in all those numbers, in the last video we discovered that the normal force was 41.3 newtons. So now that we know the normal force, we can go ahead and plug it in. And we can say that the kinetic friction is equal to the coefficient of kinetic friction times the normal force, 41.3. So our kinetic friction is equal to 16.52 newtons. So in this case, the kinetic friction is always just equal to. It doesn't matter how fast this object is moving, if the person's pulling it really, really hard, or if the person's pulling it really, really slow. the kinetic friction will always have a value of 16.52 in this case. Now, if they were to pull harder on the rope, then that would modify the tension force here, which would mess with the normal force. So if anything changes on this problem, it's always a smart idea to go back and double check to make sure that that kinetic friction doesn't get modified as well. But in this case, you've got a force acting on it, which is decreasing the normal force. So our kinetic friction ends up being 16.52 newtons. And you actually can do a little bit of calculations to see if this object is accelerating the x direction as well if you'd like to. Just keep in mind that the force in the x direction is equal to mass times the acceleration in the x direction. So what you could do is add up all the forces in the x direction and determine how fast this box is accelerating. But that's for another thing. This is just kind of a fun little thing you could do. So let's go ahead and take a look at another example here. Now we've got a box that is initially at rest. So this one's kind of bringing together the things that we've been doing. The box is initially at rest. So bam, there's a box initially at rest. Then it's pushed horizontally by a 40 Newton force. So what is the magnitude of the force of friction? Notice they don't tell us if the object is moving now. It's only initially at rest. So we can start with that static friction and we'll see what happens with that. So I've drawn out my picture here. I'm going to go ahead and do my free body diagram. Weight is going down. Normal force is going up. I've got the force applied here. And then I've got friction acting in this direction. So X and Y. Standard labeling, positive, positive, negative, negative. So in the X direction, I have the applied force, applied force in the positive direction, and I've got friction in the negative direction. In the Y direction, I've got the normal force acting up, and I've got weight acting down. In this case, just like in our first situation, the object is not moving in the X or the Y direction. Sorry, it's not moving in the Y direction. So that means that the acceleration in the Y direction is going to be 0 meters per second squared. The person is only applying a force directly to the right, which means that the Y direction is not modified at all. So that I know that the sum of all the forces in the Y direction also has to be 0 newtons. Another thing that's different about this problem is they give us the weight of the object. So in the previous problems, we've been given the mass and we had to calculate the weight. But in this case, they already tell us that the weight of the object is equal to 75. So as I'm doing some calculations, I need to keep that in mind. Don't know why that arrow is messed up. So the normal force is equal to the weight, which again, I just said the weight is 75 newtons. So the normal force is 75 newtons. This is excellent because now we can go ahead and try and figure out that force of friction. The whole reason we found that normal force was because we know that friction, if it's static, is less than or equal to mu n, and friction, if it's kinetic, is equal to mu n. So let's go ahead and try and make the assumption that the object is still at rest. If it's still at rest, then I'm dealing with static friction. So I'm going to take a moment and find out what the static friction is. The static friction is always less than or equal to the mu, which is 0.5, 0.5, times the normal force, which is 75. Which means that my static friction, is less than or equal to 37.5 newtons. So just like in the first question, I'm asking myself, is the object going to start moving? Well, if I'm applying 40 newtons of force, that is enough to break static friction. So I know that I'm not dealing with static friction. So let's take a look at the kinetic friction. Again, kinetic friction doesn't matter how much or how fast the object is moving, or it doesn't matter how much force is applied to it. Kinetic friction, if an object is sliding, then it has a kinetic friction equal to mu n. So Fk is equal to the coefficient of kinetic friction, 0.3, times the normal force, 75, and our kinetic friction is equal to 22.5 newtons. So because static friction broke, that means we're no longer dealing with static friction, and we have to deal with kinetic friction. So that is going to be our force of friction. That's the magnitude of the force of friction there. And again, it's because we broke the static friction. We applied enough force to say, for static friction to say, I'm done, I can't deal with this anymore. Kinetic friction, you start taking over. Object starts to move, and kinetic friction does 22.5 newtons of force in the opposite direction of the applied force.